Hello and welcome to this video about math done on computers. In this video we'll be writing a computer program that can calculate the first n antiderivatives of the error function. So this is what the error function is. It's defined to be the first antiderivative of the bell curve function given by this exponential. I'm going to write it out in functional notation like sine or tangent to make it easier to read. I like to say antiderivative because an integral implies upper and lower bounds, which this function doesn't come with, and with polynomials added onto the end representing the constants that integrals come with. Antiderivatives are much harder to calculate than derivatives because they don't come with nice rules that derivatives have. Like there's no easy product rule or chain rule for concatenated functions. We'll assign this blue letter E to be equal to the bell curve exponential function because it will be easier to work with this function in this way. This is the first derivative of this function, and the first derivative of E can be written in terms of itself like this. We'll assign this pink f to be equal to the error function, and the first derivative of the error function is equal to the bell curve function by definition. So now to calculate the derivatives of these terms to help us to find the antiderivatives of f later, we'll set w to be equal to the error function multiplied by an integer power of x. Now to calculate the derivative of this term, we'll use the product rule here. Then we'll evaluate all of the functions we're differentiating in this expression to give us this expression, which is in its most simplified form. Now to find the first derivative of this term, the bell curve exponential function multiplied by x raised to the power of an integer. We'll expand it out using the product rule. Then we'll evaluate all of the derivatives. Finally, we'll simplify this expression to give us this expression. So I'm going to make a claim that all of the antiderivatives of f can be written as finite polynomials of x multiplied by f and e, so that we won't be in need of any more functions like f that we'd need power series to calculate. And this term can be written like this, with only two terms multiplied by f. I'm not going to prove it directly, but I am going to use this fact to get the antiderivatives of f to any finite value. It should already be clear from the calculations of w and v done on the previous page. We're going to show it to be true as we calculate methods to find these antiderivatives that we'll use to program the computer. This should make our calculations of the antiderivatives much easier and even possible. So firstly we need to calculate tables of these terms, f multiplied by power of x and indexed by this power of x, and similarly for e multiplied by power of x. So we'll start with an indefinite value of n and differentiate this term containing f and expand it out using the product rule. And evaluating all of the differentials gives us this equation. We'll increment n by 1. We'll then multiply this equation by this fraction so that an arbitrary constant value may be placed in front of the first term on the right-hand side. And so this expression's antiderivative is this term. And we can write it out in antiderivative notation like this rather than in integral notation. We similarly need to find a table of antiderivatives for xn multiplied by e. We'll start with an arbitrary term of this form and get its derivative and expand it out using the product rule. We'll evaluate the derivatives. Then we'll simplify this expression. We can already start to write it out in antiderivative notation. Then we can decrement n by 1. We'll multiply the whole expression by this fraction so that the term with the highest power of x will have a coefficient of c. And so this is what this equation is. We'll use this equation to calculate the antiderivatives of all these terms. Now to look at how to find the antiderivative of a term containing f and a power of x by hand. I'm using another color coding scheme, so I'll leave e and f black for now. It's good to look at the algorithm before I show you the computer program that does it. So using this differential equation, we can calculate that the antiderivative of this expression is this. But to make the equations correct, we need to balance it by adding this term to the right. So we need to eliminate this term. So we'll do this by adding the opposite of this term to the left, and they should cancel. We'll use this differential equation to add this term to the antiderivative at the top, and to balance this equation so that it is the derivative of the top equation, we'll add this term onto the right. So then we'd subtract this term from the right to eliminate this term from the bottom equation. And using this differential equation, we'd place this term into the antiderivative expression, and so keep repeating these steps until all of the extra terms in the bottom equation cancel out, so that we're just left with the first term. And so here's the next example. We have to find the antiderivative of this term. We'll use this differential equation to determine what goes into the top line. And so we've got to add this term to the bottom line to balance this equation, so that the bottom line is the derivative of the top. Then we have to add this term onto the end to eliminate it from the bottom equation. We'll then use this differential equation to add this term to the top equation. Then we'll add this term to the bottom to properly balance it. Then we'll eliminate this term by adding this term to it. Then we'll use this differential equation to add this to the top, and there's nothing else left over to add to the bottom equation. So we've done it. The top line is the antiderivative of x to the power of 5e. So now we'll work through a third and longer example. We'll have to find the antiderivative of this term. So we'll use this differential equation to get the term in the top equation. And to keep this expression correct so that the bottom expression is the derivative of the top expression, we'll add this term to the bottom. So now we'll have to subtract this term on bottom to eliminate it. We'll use this differential equation to determine what goes on top. And we'll add this term to the bottom to make the second equation equal to the derivative of the first. And then we'll subtract this term to eliminate it. We'll use this dE to find its antiderivative to go on top. And we'll add this term to the bottom to keep this system of equations correct. Then we'll subtract this term to eliminate it. And we'll use this dE to determine what goes on top. And we'll add this term to the bottom to keep this system of equations equal. Then we'll subtract this term to eliminate this term from the bottom. I've decided to start a second line for this equation because I've run out of room. Then we'll use this differential equation to determine this term's antiderivative to go on top. Then we'll add this term to make the first equation equal to the antiderivative of the second. Then we'll subtract this term to eliminate it. Then we'll use this dE to determine what goes on top, and there's no other term to write on the bottom, and all of these terms cancel. So that's it. We found the antiderivative of the term circled in red. So this is the data structure that we'll be using to store the table of antiderivatives for functions that are x to the power of n times f. A list of terms making an expression with a list of pointers to the start of each expression, and I've written what the derivatives are of these expressions underneath. And this is the data structure that stores the antiderivatives of x to the power of n times e, which is the same data structure but storing different information. This is the algorithm we'll use to find the next element in the table. We've got to fill out the third expression in the array. We'll use the algorithm that's been described earlier to get the antiderivative of x squared times f and place it into the construction array. It doesn't need to be simplified, but it's good to place it there in case something needs to be done to it. Then we'll copy it to the table and set the pointer variable to point to the start of it. And this is the data structure to store the antiderivatives of x to the power of n times e. It's similar to the previous table. So this is the function that finds the antiderivative of any term of the form x to the power of n multiplied by e or f. It was originally only meant for the first type of term, but expanded for x to the power of n multiplied by e. The power of x is passed by the parameter n, and whether it is multiplied by e or f is passed by the parameter efi. So we'll set the initial quantity that we want to antidifferentiate here. And these are some indexing variables used in the loop. K is used to prevent infinite loops. And we'll use a while loop with a non-termination variable that will be set to true when we've finished antidifferentiating the term. And if the term that we're up to or starting with has this form that is circled here, then we'll set these variables that determine what goes into the antiderivative expression. This code is executed if the term is a multiple of f, or the error function. And these variables are what go into the expression on the bottom line that we're antidifferentiating. It now has an e at the end instead of an f. So this is the code that we enter if the term is a multiple of e or the bell curve function. We'll set the variables for what gets added at the top and bottom here. This is an expression that's just the scalar multiple of e. Its antiderivative is a scalar multiplied by f. And because it doesn't produce a term on bottom, it's a terminating term. And so we'll set the termination variable to be true, to escape the loop and finish. And this is another type of expression that's a multiple of e and x raised to the power of 1. That's just an x, and it will produce a different term to be added onto the antiderivative, which is a scalar multiplied by e. And just like the conditional statement above it, it sets this variable to be true, so as to escape the loop and finish. And this code is entered when e is multiplied by x raised to the power of 2 or higher. It produces a term to go on top and one on bottom, and continues the cycle through the loop. And here is where we'll set the value of the antiderivative constants in the construction array, so that we can simplify it later and store it in a lookup table. And the value of the term to be added onto the bottom is just passed onto the main variables. These values aren't going to be stored in any table. And here is where we'll increment the indexing variables. They seem to be the same all the time, even if they perform different functions. And we'll set the length of the expression here. Here are two functions to make up the lookup tables. There are two tables, one for e and one for f. We'll call the function to get each antiderivative for each term, and they don't need any simplification. They can be just copied into the table. And here are the functions to copy the expressions from the construction array into the lookup tables. So we'll need to do some error checking. We'll check these tables by doing a symbolic differentiation of all of these expressions. The second function is similar to the one I made in my video on finding the nth derivative of the error function. The first one is different but uses the same techniques and is worth having a look at. So this is the function I'll be using to get the derivative of each expression in the lookup table. It calculates the derivative and stores it in the construction array so that it can be looked at and checked. So firstly we'll declare the function and get the pointer to the start of the expression in the array and set it equal to start. Then find the pointer to the last term in the array and set it equal to end. We'll now make a for loop with an extra variable k to avoid infinite loops. Then we'll load in these variables from the table of derivatives. If the term has an e in it, we'll place these variables into the construction array. And if the term has an f in it, the only other option, then we'll place these variables into the construction array instead. Here is where we'll place these two terms into the construction array, so that they may be simplified later. Here's where we'll increment the variable to prevent an infinite loop. And finally we'll set the length of this expression here. I made a special function to print out what is in the construction array in algebraic form, so that I can have a look to see if the calculations are correct. I'll be checking the correctness of these functions by looking at what the derivatives are for each of the antiderivatives in the table. I'll be placing these derivatives into the construction array and won't transfer them anywhere else, so I need to print out the contents of the construction array. So this is the table of antiderivatives of x to the power of n times f. the number of terms grows slowly at about n times a half, which is the same as for the number of terms in the nth derivative of tangent, inverse cosine, and the error function. This is the table to find the antiderivative of x to the power of n times e. It's similar to the last table, only the coefficients remain a bit more simple. So I'll show you this table in advance. It's the nth antiderivative of the error function, starting with the error function in the first position. The number of terms is equal to n plus 1. The nth antiderivative has n plus 1 terms, and the constants look ugly. I haven't written them out in full because they take up too much space. This is the data structure used to store this table. I've shown it for the first 4 expressions. So this is the algorithm that we'll be using to find the nth antiderivative of f. We'll use an example. We'll get the 5th antiderivative from the 4th. So this is the 4th antiderivative. We'll get the first term in this expression. We'll use the lookup table to find its antiderivative. We'll multiply it out, giving us this expression. Then we'll get the second term in the 4th antiderivative of f. We'll get its antiderivative from the lookup table. It's e this time. We have to look up e's lookup table. And this is what we'll get after simplifying this expression. We'll do the same thing with the third term. We'll use the lookup table to find its antiderivative. Then we'll simplify this expression. It has only one term and looks very simple. And we'll find the antiderivative of the 4th term. And then we'll get the antiderivative of the 5th term. So now we're ready to add them all together. So now we'll add them all together. Notice that 5 of these terms have a number times e. These can be added together. This expression isn't in its most simple form. Now we'll gather like terms together. Then we'll simplify this, and now this is the 5th antiderivative of f in its most simplified form. We can put this into the table, and use it to find a 6th antiderivative and so on. Now to write some code. This function gets the nth antiderivative of f from the previous one, the n-1th antiderivative of f. We'll get the start and end pointers to the n-1th antiderivative of f. We'll use this pointer to store the length of the nth antiderivative that we're yet to calculate. We'll loop through every term in the n-1th antiderivative of f and get the constants associated with it. We can use the variables m and ef to find its antiderivative in the lookup tables. If the term contains an e, then we'll look it up in the e lookup table. And if it contains an f, then we'll get its antiderivative in the f lookup table. So we'll copy every term at this location in the lookup table into the construction array. If it's in the e lookup table, we'll get these constants for it here. Otherwise, it will be in the f lookup table, and we'll get these constants for it here instead. We have to multiply these expressions by the constant found earlier. I thought I'd do it here because it takes up less memory in the code. So then we'll copy this expression to the construction array, so that we can simplify it later. We'll copy everything here, like in the algorithm that we studied earlier. The variable ptr is used to help keep track of where to put the next term in the construction array, and not just for the final length of the expression. So now we've finished. We'll copy the length of this expression here. We'll increment the number of elements in the antiderivative table here. Then we'll set the start and end pointers to this nth antiderivative of f here. We'll have to redo them later. So this is the function that is used to find the first n antiderivatives of the error function f and place them into a table. We'll start by placing the first entry in the table here, which is f itself, and set its starting position and length here. And we'll set the number of entries found so far to be 1. And we'll make up a loop to get the rest of the entries by induction. This function gets the next antiderivative from the previous one. We've just studied it in this video a few moments ago. Then we'll simplify this expression using these functions. I've described them in earlier videos. Then we'll set the number of terms in the ith antiderivative that we're calculating now. Then we'll copy it to the table from the construction array, here. And in this function we'll put it all together. It creates all three tables and tests the last one, and then prints it out. It tests each antiderivative 1,000 times and goes very fast. And this is the function that tests that the table is correct. We need to set this constant because the error function is defined differently in JavaScript, being equal to the antiderivative of e divided by this constant. So we'll have to multiply it by this constant during the running of this function. We'll write a message that testing is in progress. The input variable must be in range. We'll get the start and end positions of two expressions next to each other in the table, so that one is the derivative of the other. We'll make up a loop to test it n1 times, which could be up to 1,000 or just 1, depending on how much you've debugged it. We'll get a good range for the input variable here, which we'll call r for random. It's good for it to be not too close to 0. We'll get two variables that are extremely close to r, and that will be used for numerical differentiation. Then we'll calculate the value of e or bel for each of these variables. And then we'll get the error function for each of these variables. This will be an accumulated value which will have numbers added to it during the cycle of a loop, and so is initially set to 0. We'll make up a loop to evaluate the value of the antiderivative lower down the table. So we'll get the constants for each term in the antiderivative expression. This is what the value would be if its trailing variable is e. And this is what it would be if its trailing value is f, and it would be added onto the value variable. And this is where we'll get the value of the antiderivative further up the table, and then use numerical differentiation on it, so we'll need two variables. We'll make up a table to go through every term in the antiderivative. We'll get each of the constants for each term, and if the trailing variable is e, then we'll calculate the value here. Otherwise, if its trailing variable is f, then we'll calculate its value here. And this is the numerical differentiation step. So we'll get the absolute and relative differences here and get the smallest one. If the difference is too large, then we'll return an error with all of these variables that will help us to debug the code. And then we'll display a message that testing has finished. This is the function used to print out the table of the antiderivatives of f. I've explained one in a video called Print Tangent Table. And so I'll just show you this table of antiderivatives of f here again. The number of terms grows as n. The constants get smaller and look very messy. They become very messy fractions with large numbers. I wrote them out to 4 significant figures only, but the computer could store the value to hundreds of decimal places. I felt that it was good that a second power series function need never be made. When it was done the first time, people thought it would have to be done all the time. I hope that this information can help you make computer programs to number crunch your data better. So I hope that you have enjoyed this video and have found it to be helpful and insightful. Please let me know about any interesting thoughts in the comments. Please click like and subscribe if you like this video. Feel free to share this video, and thanks a lot for watching.